So inequalities. And the idea of inequalities, they were not equal. And instead of limiting our answers to just something with only one answer, the example that we use would be something like x is greater than 3. We said there are a lot more possibilities here. Like x could be 4. That would work. X could be 5. X could be 6. All these numbers are greater than 3. And again, in the real world, inequalities actually rule, meaning you don't just say to your parents, I wouldn't, Mom, give me $10. You should say, Mom, can I have more than $10? I'm going out to the movies. I need more than $10. Our example was at Magic Mountain, where rides are 48 inches and above. When you guys go to the supermarket, let's say you only have $20. Does it mean you have to spend exactly $20? No, you can only spend up to, so anything less than $20. But you can't spend more than $20 because you don't have it. So we drew this on a number line. And a couple of things to note is that here is x is 3, but we use a solid or dotted circle to reflect that. So a hollow or solid. So since we are not allowed to be on 3, we use a hollow circle. And x is greater means we go to the right. And that's what you guys were asked to graph the other day. Now, today what we're going to do, we're going to talk about our operations that we learned before to solve for x. We're going to do one-step operations. And one-step operations, we're going to deal with addition, subtraction, multiplication, and division. Okay? And these guys have a special rule to them for inequalities. So let's do our addition and subtraction first. So if we say x plus 3 is greater than 5, in your head, can you make up numbers that might work? 6 plus 3, right? X could be 6, because 6 plus 3 is 9, and 9 is greater than 5. You can say 10, because 10 plus 3 is 13, and 13 is greater than 5. Maybe you can say 100. Oh, great. 100 plus 3 is 103, and this is greater than 5. So we have a lot of possibilities. But instead of randomly guessing, we want to solve for x like before. So we'll say we're going to solve for x. So we have to get rid of our 3. So that's how my brain is running. I see I want to solve for x. I want to get rid of 3. Now, the cool thing about inequalities is that we can treat them like equal signs. I'm going to rewrite this again. X plus 3 is greater than 5. To solve for x, we're going to minus 3 to both sides. That's a skill that we practiced already. The opposite operation of plus 3 is minus 3. X is greater than 2. Now, this is our definitive answer here. As long as x is greater than 2, this would make our original problem a true statement. So if I plug in, give me a number that's greater than 2. Well, didn't we say 6? That was a true statement. Didn't we say 10? Well, 10 is greater than 2. That worked for us here. Well, 100 is greater than 2. That also worked. But let's try a number that isn't greater than 2. Well, what about 0? If x equal to 0, well, 0 is less than 2. So 0 is not greater than 2. And turns out, if I plug in 0 to the original problem, 0 plus 3, is that greater than 5? Not true. So one reason why we want to solve for our answer, x, it tells us instead of us wildly guessing values here, we know definitively that only numbers that are greater than 2 would give us true statements. So 3 would work, 4 would work, 5 would work. All these would work for my original problem here. Try 3. 3 plus 3 is 6, bigger than 5. 4 plus 3 is 7. 7 is bigger than 5. 8, all the possibilities above 2 work. And that gave us, we knew that from this by solving for the variable x. Now, what doesn't work? We said, well, 0 isn't greater than 2, and 0 plus 3 is 3, and 3 is not greater than 5. -1 isn't greater than 2, and -1 won't work either. So when we solve for the variable, it makes it a really nice answer that is true for all the problem. So let's try another one. What if I say subtraction? If I say x minus 6 is less than 4. So what's the opposite of minus 6? Opposite operation of minus 6 is plus 6 to both sides. X is less than 10. So instead of us randomly guessing numbers that would be true for this equation up here, we have a definitive statement. Only numbers less than 10 would make this a true statement. So we can try. Let's pick a number less than 10. Let's pick 9. 9 minus 6 is 3. That is less than 4. Another number that's less than 10, let's say 5. 5 minus 6 is -1. Isn't -1 less than 4? Yeah. How about 10? 10 minus 6, is that less than 4? Well, 10 minus 6 is 4, and is 4 less than 4? Not true. So we found the last answer that was really close that actually doesn't work. But if I try this, if I say, what about 9.9? Here is 0, here is 10, and numbers that are less than 10. Isn't 9.9 less than 10? Let's draw this as a hollow. So we try it. 9.9 minus 6, would that be less than 4? 9.9 minus 6 is 3.9. Hey, and 3.9 is less than 4. This is a true statement. This is totally true. So what we're trying to figure out is up to what, like, what's that borderline? What can I get to still make this a true statement? Okay. So addition and subtraction aren't anything new. Let's look at two quick problems real quick again. If I say x minus 5 less than 4 and 6 plus x is greater than or equal to 2. We have two different problems here, two different examples. So for my problem on my left, I want to solve for x. Opposite of minus 5 is plus 5 to both sides. X is less than 9. So we treat these just like what we worked on before, as if they're equal signs. My next problem, minus 6 to both sides. This one is greater than or equal to, but again, we treat it like an equal sign. X is greater than or equal to -4. 2 minus 6, you have $2, you owe me 6. When you pay me back, you still owe me 4. Okay, so let's work on multiplication and division now. So multiplication and division. Now for multiplication and division, we have some special rules. And the rule is this: if you divide or multiply across the inequality, comma, you must flip the inequality. Okay. If you divide or multiply across the inequality, you must flip the inequality. Now let me show you an example of this. If I say negative 3x is greater than 9. To solve for x, we have to get rid of the -3. -3 is multiplying x, so we're multiplying x. Opposite of multiply is divide. Divide both sides by negative 3. Okay. So we have x, those divide out, and becomes a positive x. And we have a negative 3 on the right. Now this is what you want to make sure you do. Okay, make sure you then, if we multiply or divide across, in this case we divided across by negative. Everyone say that we divided. That means we must flip the inequality. This inequality changes from a greater than to a less than. Okay, so that's the general rule. Let me show you one more time. If I say negative 5x less than or equal to, let's say 10. We want to get rid of the negative 5. Opposite of multiply by negative 5 is divide. So I'm drawing my division sign on both sides. The 5s and the 1s cancel out to become 1. And we're left with x and negative 2. Did we just divide or multiply across by negative? We did. So we had to flip your inequality. Oh, sorry, I didn't flip it. I don't know why. We had to flip your inequality. Now, let's test if this rule makes sense. Why do I have to flip it? So let's draw the answer here for my first problem. X is less than negative 3. So let's draw a number line. Here is 0. Here's negative 3. It's hollow. And less than negative 3 would mean we would shade to the left. Okay, so all the answers on the left are going to be true. So an example of this would be negative 4, negative 5, negative 6. Everyone okay with those possibilities? So negative 4 is less than negative 3. Negative 5 is less than negative 3, and negative 6. So these are all our possible answers. We have a lot. Now, would this make negative 3x greater than 9 still be true? Try, plug in negative 4, plug in negative 5, plug in negative 6, okay? What is negative 3 times negative 4? That's going to give us 12. And 12 is greater than 9. It worked. If I plug in negative 5, negative 3 times negative 5 is 15. And 15 is greater than 9. It worked. Negative 3 times negative 6, that becomes 18. And 18 is greater than 9. Yeah, all these possibilities work. And this is only true because I flipped the inequality. Whoops. Yeah, other way. It's because I flipped the inequality. I flipped the inequality to make this work. Now, I'm going to make a mistake. On my next problem, I'm going to make a mistake. I'm going to say negative 2x is less than, let's say the number is going to be 8. Okay? The way we would solve this problem is we would divide both sides like normal by negative 2. And we end up with the answer x less than negative 4. Now, please be aware that this is wrong. That's going to be wrong, okay? Wrong. But let's double check why it's wrong. Just because I say it's wrong, well, let's double check. Give me a number that's less than negative 4. Let's draw my number line again, just so you guys can visually see it. Here's 0, here's negative 4. And pick a number that's less than negative 4. Negative 5, negative 6, negative 7, okay? So negative 5 is less than negative 4. Negative 6 is less than negative 4, and negative 7. These are all going to work. But when I try testing it, negative 2, x becomes negative 5, right? X equals to negative 5. We said it should work, but does it really work? Is negative 2 times negative 5 positive 10? Is 10 less than 8? No, that didn't work. Is negative 2 times negative 6, is this less than 8? No, that's 12. 12 is not less than 8. So the idea is that because when I move over that negative sign, if I don't flip the inequality, it doesn't give me right answers. It's actually totally wrong. And I liken this to this. Inequalities aren't just one answer. It is a range of answers. So think of a basketball team. This is a basketball team. Team 1 and Team 2. Team 1 and Team 2. And let's say Team 1 has the worst player in the school there. So see, that's why they're less than 8. Worst player in the school. If you move that worst player to the other side, doesn't the other side become the worst player now? And that's what a negative does. It makes all your goods sound terrible. Think of a time when your mom was mad at you. No matter what you do, she's still mad at you. There's that negative filter on it. So what happens is a negative sign changes any number from a positive number to a negative. All of a sudden it makes it weak. So we want to flip that weakness over. So let's do this problem again. I'll show you this illustration. -2 is x is less than 8. So when I bring that weakness over, when I divide by -2, I'm going to bring the weak player with me. So instead of my left side being weak, see how that's the left side? When we move it over, x, and that's -4, now the right side is now the weakest side because of that negative sign. Imagine you saw this much money in your bank account. You open your bank account one day and you see that. Okay? The thing about a negative sign, it's so powerful because if I just draw this in front, you went from really rich to really poor. And that's what happens to this negative sign. When I divide it across here, it made the right side really poor. Just by, not just numbers, by just a flip of a sign. So we have to make sure we flip that inequality with us. Okay. This also works with multiplication. So let's look at this with multiplication. So if we use x over negative x over 2 is less than 3. Negative x over 2 is less than 3. So make a decision. What variable are you solving for? I'm solving for x. Solving for x. I need to get rid of a -2. What is the 2 doing? It is dividing. The opposite of division is multiply. So I'm going to write a multiply by -2 to both sides. Again, it's like me taking the weakest player and moving the weakest player from one side to the other. So this becomes the 2's divide out. So we're left with just x now. X and -6. And we have to flip to account for that weakest player. So when does this rule happen? This rule only happens, let's read the rule on top, only if you divide or multiply across the inequality. You have to flip the inequality. If you're adding or subtracting, no problem, that's totally okay. Only when you multiply and divide. Only when you multiply and divide. Okay? And that's one of our big rules, and that's our big takeaway.